Hello everyone, I would like to welcome you all to the ISRO 2025 PYQ series powered by ACE Engineering Academy and ACE Online, and today's subject is power electronics. Myself Rajendra Garashe, I have done MTech from Indian Institute of Science, Bangalore. I was all India 7th ranker in the GATE examination, right? So friends, today we are going to discuss the previous year questions from ISRO examination for the subject power electronics, right? So before proceeding, please confirm, is my voice clear? Is my screen visible? Please give confirmation, guys. Is my voice clear? Yeah. Yeah, please give confirmation. Is my voice clear? Yeah, fine. Thank you. Thank you. Right. Yeah. So let us begin the today's session with the first question. This question is from 2013 ISRO examination. Use of a reverse conducting thyristor in place of anti-parallel combination of thyristor and feedback diode in an inverter, and there are various options. Effectively minimizes the peak commutating current. Second, decreases the operating frequency of operation. Third is minimizes the effect of load inductance on the commutation performance. And fourth is causes the deterioration in the commutation performance. So here he is comparing about the reverse conducting thyristor, and second is its equivalent. Reverse conducting thyristor means it is equivalent to a thyristor and a diode connected in an anti-parallel. Thyristor and diode connected in an anti-parallel case. So how it will affect, let us discuss, or what is the difference, let us discuss. Check, in case of thyristor and a diode, if I connect in anti-parallel, yes, of course this should be the diode, not the thyristor. Yes. So this is a thyristor and diode anti-parallel, right? In this case what happens, generally in order to turn off the SCR, what is the requirement? Recall the dynamic characteristic of SCR during turn off. At that time the conclusion is, or in that characteristic the conclusion is, in order to turn off the SCR, first of all reduce the current from the SCR below the holding current value. But only reducing the current below the holding current value is not sufficient to turn off the SCR successfully. In addition, we need to maintain the reverse voltage also across SCR. So what happens in this case, when SCR is in a conduction mode, no doubt your reverse conducting thyristor and this equivalent both will be having the same operation when SCR is in a conduction mode. But when SCR, we want to turn off the SCR, then what happens, if I maintain the reverse voltage here in this equivalent circuit, if I maintain the reverse voltage across my switch, then this diode will start conduction, and when diode starts conduction, automatically the on state voltage drop. Think in practical way, when this diode starts conduction, automatically this on state voltage drop of a diode will appear as a reverse voltage across the thyristor. Means on state voltage drop of a diode will appear as a reverse voltage across the thyristor. So that's why my thyristor will go in a successful commutation mode, because to turn off the thyristor we need to maintain the reverse voltage also. Whereas in reverse conducting thyristor, what will happen? In reverse conducting thyristor, if you maintain the reverse voltage, then as the thyristor is reverse conducting thyristor, then your thyristor will go in a conduction mode, that RCT. I am not saying about the conventional SCR. I am talking about the reverse conducting thyristor, right? So here what is happening, if I use this diode in case of yes, if I use a reverse conducting thyristor in place of this combination, then what will happen? It will create a deterioration in the commutation on the performance of your device. Means they are comparing this equivalent circuit with the reverse conducting thyristor. And now the question is, when this equivalent circuit is replaced with the reverse conducting thyristor, then what will which one of the following is correct, they are asking, right? So what happens here, when I connect thyristor and diode anti-parallel, when we maintain the reverse voltage, automatically this diode will start conduction, and this on state voltage drop will appear as a reverse voltage for thyristor. So therefore my thyristor will go in a conduction mode successfully. But whereas in reverse conducting thyristor, when you maintain reverse voltage, that will again go on conduction mode, right? So reverse voltage will not be maintained automatically, right? So therefore that will causes the deterioration in the commutation performance. So option D is the correct option. All right. Yeah. Next. Yes, this question is from 2014 examination. A waveform shown as input is applied across the primary of a pulse transformer which has 1:1 turns ratio. Turns ratio is 1:1. The output on the secondary side will be as shown in the figure. Yeah. So this is the input voltage they have given, right? Pulse transformer, it is like simple isolation type transformer. Generally in power electronics, we are using the pulse transformer in order to provide the isolation between low voltage supply, which is connected at a control circuit of your power semiconductor device, and high voltage supply, which is connected at a load circuit of your power semiconductor device, right? So if I provide this type of input voltage waveform to the primary of the pulse transformer, then how will be my output voltage waveform? That is at a secondary side waveform they are asking, right? Now we know transformer is equivalent to your inductor, right? And we know in case of transformer, voltage, that is secondary side voltage I am writing, or let me write it as V2 is equal to minus of, you can use this as L into di by dt, or in other way you can write it as like this also, E2 equal to N into d phi by dt, negative, or it is minus of d by dt of flux linkage. N phi is a flux linkage. All right. So further we can write this as a N phi. I can write this as minus of d N phi upon di into di by dt, and that d N phi upon di is nothing but your inductance. So it is minus L into di by dt. Ultimately it will come as minus L into di by dt. All right. Now here tell me, if I am having this type of the waveform for the input, right, then what is the differentiation of this waveform? Check here, and here one negative sign is also present, be careful. So here this is my what I can say, this is like a pulsating waveform. The differentiation of pulsating waveform, I will be getting this type of waveform. I will be getting this type of waveform. Check here. If you check from this point to this point, your di by dt will be positive, right? So here higher, here lower. So that's why di by dt will be positive. So I will be getting positive. Next, from this point to this point it is 0. And next from here to here again it is decreasing. So right, so we will be getting again this type of the pulse, right? So here if I check, here it is positive, here it is negative, but here in this case it is showing only positive. Here it is also only positive, but I want in terms of positive and negative. In option C you can check, it is negative, here it is also negative, but in option D what is happening? It is having negative, positive, negative and positive. If I take differentiation of this will be, I will be getting this type of waveform. I am drawing here for differentiation. This is differentiation of this waveform. Now we are having one negative sign also, right? So if I multiply this with -1, I will be getting which type of waveform? I will be getting this type of waveform. So correct answer is option D. All right, option D is the correct option. Yeah, it is simple, actually basic question. Strictly speaking, it is not related to the power electronics, but as here they have used the word pulse transformer, so that's why we have taken it as under power electronics. All right. Yeah. Yes, this question is from 2014. And SCR triggered by current pulse applied to gate cathode can be turned off. Yes, this is OWF, off. Yes. Tell me, when SCR is triggered by a current pulse, means by using the gate signal, we have turned on the SCR. Then how to turn off the SCR? And they have given the options. By applying a pulse to the cathode, by applying a pulse to the anode, by applying another pulse of opposite polarity to the gate cathode, and fourth is by reversing the polarity of the anode and cathode voltage. Come on, tell me, if my SCR is in an on state, already I have turned on the SCR by circulating the gate current, then how to turn off the SCR? They are talking about SCR, silicon control rectifier, right? SCR means you need to take only SCR, that is conventional thyristor, right? Yeah. So here, if you check, if I want to turn off the SCR, what I need to do? I need to maintain the reverse voltage across SCR. So option D is the correct option, by reversing the polarity of the anode and cathode voltage. All right. Yeah, simple question. Okay, because if you check, by applying a pulse to the cathode, is it anything related to the SCR? No. Second, by applying a pulse to the anode, not at all. By applying another pulse of opposite polarity to the gate cathode, no. If the question is like GTO, suppose instead of SCR, if the question would be like and GTO, if the question is like a GTO, then you can say by circulating positive gate current we can turn on, but by circulating negative gate current we can turn off. But be careful here, the question is related to the SCR. So correct answer should be option D. All right. Yeah. Next, 2014. The ripple factor of a full wave rectifier circuit compared to that of half wave rectifier circuit without filter is. So they are asking the ripple factor comparison between a full wave rectifier and a half wave rectifier. Yes, full wave and half wave rectifier circuit. So here they have not specified anything about whether it is a controlled rectifier or uncontrolled rectifier, etc. So simply here we are going to assume it is an uncontrolled rectifier. All right. So tell me, in case of single phase full wave rectifier, yes, single phase full wave rectifier, FWR means full wave rectifier. Yeah. How is the output voltage waveform? Yes, we will be getting this type of pulse. Fine. Correct? For this waveform, what is the V0 RMS? It is same as that of Vs RMS, that is Vm by root 2. All right. And what is the V0 average? V0 average is equal to, yes, 2 Vm by pi. Average is 2 Vm by pi and V0 RMS is Vm by root 2. Right. Now what is the form factor? V0 RMS upon V0 average. So we can write it as a Vm by root 2 upon 2 Vm by pi. So here Vm cancel out, we can get it as pi upon 2 root 2. Right, pi upon 2 root 2. This is form factor. And what is the ripple factor? It is under root form factor square minus 1. Yes, REF under root form factor square minus 1. Now put the value and tell me what is the answer you are getting for this. Yes, under root pi upon 2 root 2 square minus 1. Yeah, simplify this, you will be getting it at 1.211. Please check once. It is simple calculation only. Right. Next, second is half wave rectifier. Single phase half wave rectifier corresponding to 0 to 2 pi will be getting one pulse only in the output voltage. So my V0 waveform will be like this. Fine. So V0 RMS, yes, Vm by 2 and V0 average, Vm by pi, right? This is half sinusoidal waveform. And form factor, V0 RMS upon V0 average. Yes, it is Vm by 2 upon Vm by pi. So it is equal to pi by 2. Fine. And what is the ripple factor? Under root form factor square minus 1. Yes, so it is 0.483, right? This is the ripple factor in case of half wave rectifier and in case of full wave rectifier. Now compare these two and tell me the suitable option. Come on. For ripple factor of half wave rectifier, it is 0.483 and in full wave rectifier it is 1.211. So what is the correct answer? Yes, can anyone? Yes, so can I say that if I compare these two, then I will be getting it as a is it a half of that of a half wave rectifier? No. Less than half that for a half wave rectifier circuit? Yes, less than half that for a half wave rectifier circuit. Check. Here it is 0.483, here it is 1.211. Correct? So which one is correct? A suitable option is option B. Fine? Yeah. Check, it is only the comparison of the values. That's it. Next, an ideal rectifier should have transformer utilization factor of 1. If the actual transformer utilization factor is 3.5, it shows that. Yeah. So transformer utilization factor, it indicates your V0 RMS into I0 RMS divided by, means it is a ratio of load power to the Vs RMS into Is RMS. Means this Vs RMS into Is RMS, it indicates your transformer rating, and based on the transformer rating we decide the size of the transformer, right? More the rating of the transformer, definitely more is the size. All right, now tell me, if transformer utilization factor is a 3.5, if this is equal to 3.5, means V0 RMS into I0 RMS upon this, I am writing it as Vs RMS into Is RMS means this ratio is right, load power is 3.5 times my transformer rating. Means indirectly I can say that in this case I require a transformer which is having a VA rating 3 times, right, that of your load rating. Means here we require the size of the transformer that should be greater than 3 times, means it is 3 times larger than the actual size. In ideal rectifier, the transformer utilization factor should be equal to 1. Means my power consumed by load and my transformer size should be equal. But in this case, power consumed by load is 3.5 we are getting. So that's why it is transformer size should be 3.5 times larger, right? So option B is the correct option. And next, a power MOSFET is, this question is from 2017. Yeah, a power MOSFET, whether it is a voltage or current control device, it is a voltage control device. So correct option is option A. Power MOSFET is a voltage control device. Next, 2017 question. When thyristors are used in series or parallel, a snubber circuit is. In SCR, why the snubber circuit is used? Yes, in protection of SCR we are having the various protections. Which are those protection? Over voltage, over current, dV by dt and di by dt. For over voltage, what we are using? For over voltage, thyristor, right? For over current, fuse, FACLF, and circuit breaker. Next, for high dV by dt, RC snubber, and high di by dt. For high di by dt, inductor, right? So here they are asking about the snubber circuit. The snubber circuit is used to limit the dV by dt. All right, to limit the dV by dt. Yes. Next, this question is from 2018. A single inverter. No, actually it should be single phase inverter. Yes, please correct it. A single phase inverter has a square wave output voltage. What is the percentage of fifth harmonic component in relation to the fundamental component present in output voltage? Yes, so they are asking the percent ratio of V0 5 RMS to the V0 1 RMS. Square wave output they are saying, and our task is to find a percent V0 5 RMS to the V0 1 RMS. Yes, a simple question. Come on, during our sessions we derived the expression V0 5 equal to 1 by 5 into V0 1. Yes or no? So here V0 5 RMS is equal to 1 by 5 into V0 1 RMS. So what is the ratio? One by 5 into 100, right? So it is equal to 20%, right? 20%. We know now we are having the expression for single phase inverter square wave. What is the V0 expression? Fourier expression I am talking. V0 summation over n equal to 1357 up to infinity. It is 4 Vs by n pi into sine of n omega t, right? So this is our Fourier expression of output voltage waveform. This is for actually full bridge. Similarly for half bridge also we are having. But whether it is a full bridge inverter or half bridge inverter, in both cases V0 5 RMS will be equal to 1 by 5 into V0 1 RMS. This expression, this relation will valid for both the cases, right? Half bridge as well as full bridge. So your answer should be 20%, right? 20%. Option C is the correct option. All right? Yeah. Next. Yes, 2018 question. If a boost converter operates with a duty ratio D equal to 1, then the output voltage is. So here they are talking about the boost converter. In boost converter, if D equal to 1, then what is the output voltage they are asking? Yeah, similar bit we discussed during our sessions also. Come on, tell me. If D equal to 1, what will happen in a circuit? What is our output voltage? Yeah, can anyone? Come on, you can post your answers in chat box. Yeah, yeah, few are saying that sir it is infinite. Huh? Let's see, let's see. Yeah, based on the expression, yes, what is the output voltage expression in boost converter? Vs upon 1 minus d. So you might be saying, sir, if d equal to 1, then that will be equal to Vs upon 1 minus 1, that is equal to Vs by 0 means infinity. Huh? But this is not true. Theoretically it is okay. But tell me in practical case, if duty cycle equal to 1, come on, if d equal to 1, then what is a d? Equal to T on by T. D equal to T on by T, alright. If d is equal to T on by T, then d is 1. So 1 equal to T on by T. So can I write here? T equal to T on. Means my on time and total time both are equal. Then what is off time? Yes, what is off time? T off will be equal to 0. If T off equal to 0, means in your switch, in your circuit operation, your off time is a 0. Tell me, if off time is 0, then in boost converter what will happen? Come on, recall the boost converter circuit diagram. This is my boost converter. Yes. Tell me in boost converter, if off time is 0, means your on time will be equal to your switching cycle time. Means switch will be in on state for all time. If switch will be in on state for all time, what will happen? The current will flow only in this loop. Yes, no? Your inductor will go on charging, charging and charging. Right? Capacitor will not be getting charged. Because in boost converter, if you recall the operation, when switch is in an off state, that is during the off time of a switch, then inductor discharge and capacitor charge. Recall the boost converter operation I am saying. When the switch is in an off state, that is during the off time of a switch, my inductor will discharge and capacitor will charge. And during on time of a switch, what happens? Switch on means inductor charge, capacitor will discharge like this. But in this circuit, if D equal to 1, then off time is 0. If off time is 0 means your capacitor charging time is 0. If capacitor is not charging at all, then there is no point of discharging of a capacitor. So here what is happening? When switch is in an on state for all time, current will flow only in this loop. No current will be flowing to your load branch. So your V0 will be getting it as a 0. Please understand. V0 equal to 0. Right? So only switch will be in on state. So like this current will flow. And after some time this current will reach to very high value. That will damage your source, that will damage your inductor and your switch also. Your circuit will not reach in a steady state value. Alright? So please be careful. D equal to 1 will not give you the steady state operation. Alright? So don't think only theoretically, ki sir D equal to 1 means V0 equal to 0. No. So in practical case you need to think here. Right? So your output voltage will be equal to 0. Output voltage 0. Option C is the correct option. Fine? Yeah, next. A simple question. This question is from 2018 examination. Yes, 2018 examination. In a single phase asymmetrical half controlled rectifier. Half controlled means semi-converter. With a firing angle alpha feeds a constant current load means highly inductive load. What will the conduction angle of diodes? Yeah, they are talking about a semi-converter asymmetrical type. Asymmetrical semi-converter. And then what is the conduction angle of a diode? Conduction angle of each diode they are asking. Yes. So asymmetrical semiconverter, this is circuit diagram. We know semiconverter means it consists of 2 thyristors, 2 diodes, 2 thyristors, 2 diodes. In asymmetrical, first leg consists of both the thyristors, second leg consists of both the diodes. Load is highly inductive, load current is a constant. So here we are taking RL load and load current is a constant now. Load current is a constant. Now tell me, in this circuit, how will be your conduction sequence of devices? Come on. If I draw, yes, yeah, here same given. This is my IG1, that is gate signal to the thyristor T1, gate signal to the thyristor T2, that is IG2, load voltage, load current waveform. And here I have given the conduction sequence of devices. Alright? Yeah. Tell me, let us begin the operation from alpha. At omega t alpha, we are triggering thyristor T1. So when I trigger T1 at alpha, what happens? Plus here, minus here, T1 and D1 will conduct. Alright? Current will flow like this, Vs, T1, load, D1 and back to the Vs. What is the output voltage? V0 equal to Vs, because positive of V0 connected to positive of Vs, negative of V0 connected to negative of Vs. So V0 equal to Vs. So we will be getting V0 Vs. Which two devices conduct? T1 and D1 conduct. After pi till pi plus alpha, what happens? Supply voltage is negative. Yes, pi to pi plus alpha, supply voltage negative. Which two devices conduct? Here inductor discharge through D1, D2. Yes or no? So here D1, D2 will conduct. And when D1 conduct, your T1 will turn off because supply voltage will appear as a reverse voltage for T1. Okay. So D1, D2 conduct from pi to pi plus alpha. D1, D2. Output voltage will be 0. No doubt. At pi plus alpha, we are triggering which thyristor? T2. When I trigger T2, my D1 will turn off. Right? So D1 will turn off. How current will flow? Vs, D2, load, T2 back to the Vs. Right? Here which devices conduct? T2, D2. What is V0? You can check it. Positive V0 to positive Vs, negative V0 to negative Vs. Means V0 equal to Vs means output voltage waveform is a positive. Right? And which devices conduct? T2 and D2. Check here. T2, D2 conduct. And from 2 pi to 2 pi plus alpha, again D1, D2 will conduct. Right? Same operation. D1, D2 will conduct. Yeah. Now tell me, generally the conduction angle of any device is calculated over one cycle of supply. So my supply is completing one cycle at 2 pi. Here my supply is completing one cycle. Over 0 to 2 pi, check the conduction angle of diode D1 or diode D2. Any one diode you can select and you can check the conduction angle. Yeah. Suppose if I select the diode D1, my diode D1 conduct from 0 to alpha. After that, alpha to pi, and after that pi to pi plus alpha, right? So D1 conduct from 0 to pi plus alpha. So it is a, yes, correct, yeah, 0 to pi plus alpha. So conduction angle is pi plus alpha. Similarly, check for D2 also. D2 conduct 0 to alpha, again pi to pi plus alpha, again pi plus alpha to 2 pi plus alpha, right? Sorry, pi plus alpha to 2 pi. Okay. So here this is total is pi and this is alpha. So total is pi plus alpha. Means here each diode conducts for how much angle? Pi plus alpha angle. Check here. They are asking about what is the conduction angle of diodes. So diode conduction angle is pi plus alpha. Please, important point here is conduction angle of any device is calculated over one cycle of supply. That statement is important. Okay, you need to find the conduction angle over one cycle of supply. I am saying means over 0 to 2 pi, for how much angle your device is conducting, that you need to find. All right. So correct answer is pi plus alpha. Next. Yeah. And this question is from 2018. Yeah. In a 3-phase half controlled rectifier with constant current load and freewheeling diode, what is the fraction of cycle the diode conducts? Consider the firing angle alpha of thyristor greater than 60 degree. Yes. Here they are saying 3-phase half controlled rectifier. 3-phase half controlled means it is, don't think it as a 3-phase half wave rectifier. No. 3-phase half controlled means 3-phase semi-converter. Okay. So here three-phase semiconverter, load is highly inductive they are saying, and freewheeling diode is also present. Yes. What is the fraction of cycle the diode conducts, right? For how much fraction of cycle your diode conducts they are asking. Yeah. So alpha greater than 60 degree. Yes. Yeah. So three-phase half controlled means three-phase semiconverter. Tell me in three-phase semiconverter, how many SCRs and how many diodes are used? Three-phase semiconverter, how many SCRs and how many diodes are used? Three-phase half controlled means three-phase semiconverter. 3 SCRs and 3 diodes are used, right? And RL load freewheeling diode, right? And in this case, they are asking about the fraction of cycle the diode conducts. Yeah, they are asking about the conduction of diode, right? Yeah, but I think these options they have given for freewheeling diode. Let us check. Let us calculate for both the case, diodes as well as freewheeling diodes. Okay. Yeah, alpha is greater than 60 degree. Yeah. So tell me, if you recall the circuit operation, this point indicates alpha equal to 0 for thyristor T1. Yes, no? Next, in three-phase semiconverter, you don't have T2. We are having 3 thyristors T1, T3, T5, and diodes are D4, D6 and D2. Okay, so T1, T3, T5. So here T1 is triggered, or alpha 0 for T1. This point indicates alpha 0 for T3, and this point indicates alpha 0 for T5. Yes, 0 to 2 pi. Yes, this is your 2 pi. Yes, let me correct it. This is 2 pi actually. So alpha 0 for T1. Yes. Yeah. So here this point indicates alpha 0 for T1. We are starting from here. This is like omega T 0, right? This point is like omega T pi. Alpha 0 for T1. This point is alpha 0 for T3. And this point is alpha 0 for T5. Right. Right, alpha 0 for T5, and here it is your 2 pi radian. Yeah, tell me, if alpha is greater than 60 degree, they are saying alpha is greater than 60 degree. Yes, means suppose this pulse is of 60 degree, so I am applying the gate pulse to thyristor T1, suppose at this point. Now this is my alpha for T1. At this point I am triggering thyristor T1. Here it is T1, and this point is a alpha 0 point, and this is my alpha for thyristor T1. Similarly, alpha 0 for T3 is this point. Now alpha is greater than 60 degree, right? Yes, so suppose I am triggering thyristor T3 here. Correct. So this indicates my alpha for T3, and for thyristor T5, yeah, let me take here, and yes, it will go somewhat this side, right? So now 60 degree plus this, right? So now tell me, if I trigger thyristor T1 here, right, in output I will be getting which pulse? In output I will be getting this VRB pulse. VRB pulse first I will get. Till which point I will get here? After that, when supply try to go in a negative pulse, then I will be getting the output as a 0. During this interval my freewheeling diode will conduct. Freewheeling diode will conduct, right? Now this point is check here, 180. Yes. Yeah, this is pi by 3 pi. This point is pi plus alpha. And this point is like 4 pi by 3. Right? Check once. This point will be like 240 degree. That is 4 pi by 3. So this is 4 pi by 3. This is pi plus alpha. This is 4 pi by 3. This is the one conduction angle, one conduction interval angle for a freewheeling diode conduction. How many such intervals will be having in one cycle of supply? 2 more such, means total 3. Total 3. So I need to find this angle. This angle is pi plus alpha. This is 4 pi by 3. So I can write here conduction angle of a freewheeling diode is equal to pi plus alpha minus, this is a 4 pi by 3. How many such intervals? 3. This is my total conduction angle. Now I can write this as 3 alpha minus pi by 3, pi minus 4 pi by 3, that will be equal to minus pi by 3. Minus pi by 3 into 3, that is minus pi. Right? 3 alpha minus pi. That is a conduction angle of your freewheeling diode. Right? 3 alpha minus pi. And they are asking, yes, fraction, na? So that's why we need to take divided by 2 pi. For one cycle of the supply, my freewheeling diode conducts for how much angle? 3 alpha minus pi. Right? 3 alpha minus pi divided by 2 pi. Okay? Right. So, or you can write it as a, yes, how they have given the options? 3 alpha minus pi. Yes, check this. We got a 3 alpha minus pi upon 2 pi. 3 alpha minus pi upon 2 pi. So, which one will match here? 3 alpha minus pi divided by 3 pi. I think option C, correct? Check once. Yes. Each interval is alpha minus pi by 3 into 3 divided by 2 pi. Correct. So, option C is the correct option. So, here please listen. Even while discussing this topic in a classroom sessions, we have given alpha less than or equal to 60 degree, no conduction of a freewheeling diode. If alpha is greater than 60 degree, then only freewheeling diode will conduct. And for how much angle it conducts, for each interval is this much angle, multiply that with 3, means total conduction angle you will get, and they are asking here fraction. So, you need to divide with the 2 pi. That's it. Fine? Yeah. Yeah, next, let us discuss this question. A step down chopper operates, yes. A step down chopper operates from a DC voltage source 400 volt. Yeah, let me write it as Vs, DC voltage source Vs, and feeds a DC motor armature with a back EMF EB, which is equal to 300 volt. From oscilloscope traces, it is found that the current rises for a time Tr, which is equal to 10 millisecond, falls to 0 over time Tf, which is equal to 5 millisecond, and remains 0 for time T0, 6 millisecond in every chopping cycle. Then the average DC voltage across the freewheeling diode will be. They are asking what is the V0 average of a freewheeling diode, right? That is VDF average, not V0 average, VDF average, right? Yeah. So here they are talking about the step down chopper, and load is a DC motor. DC motor load is represented with which load? How we are modeling the DC motor? RLE load, right? Step down chopper. Right. This is Vs, switch, diode, RLE, or EB you can write, load current, load voltage, and freewheeling diode voltage, VDF. Yeah. From oscilloscope traces, it is observed that what they have given, load current increases for time Tr, falls to 0 over time Tf, and remains 0 for time T0 in every chopping cycle, right? Means this time is a TR. Yes, current increases for time TR, means this time is TR. It falls to 0 over time TF. Now this much time is TF. So whatever this instant will be TR plus TF. What is the difference between TR plus TF and TR? It is TF. And remain 0 for time T0. Means this instant will be TR plus TF plus T0. TR plus TF plus T0. Right? In every chopping cycle. Means after this again the same cycle will repeat. Then we need to find what is the VDF waveform. VDF. So here they are expecting that from the given load current you need to understand the circuit operation. They are expecting that from the load current you need to understand, not expect, you need to understand the circuit operation, and from circuit operation you should draw the freewheeling diode voltage waveform, right? Tell me, over T equal to 0 to TR, current is increasing. This current is flowing through your inductor, right? Tell me, if current flowing through the inductor is increasing, means your inductor will be charging or discharging? It will be charging only, right? Yeah. So here during T equal to 0 to TR, during T equal to 0 to TR, inductor will be charging. Now tell me, in circuit operation, if your inductor is required to charge, what is the position of switch and diode? Check here. In the step down chopper, when switch is in on state, then diode will be in off state. Current will be flowing like this: supply voltage, switch, load, and again back to the supply voltage. Then your inductor will be charging. Charging in the sense inductor is storing energy. Who is giving energy to the inductor? Your supply voltage is giving the energy. That's why my voltage across inductor I will be getting positive. So that's why current flow to the inductor, that is di by dt, I will be getting positive. Di by dt positive means current will be increasing. Alright. Now tell me, here inductor is a charging. During this interval, switch is in a on state, diode will be in a off state, inductor charging. If inductor is a charging, then what is a VDF? Diode is in off state, right? Yeah. DF or D, anything you can write. So what is the voltage across diode? When switch on, what is the voltage across diode? Come on, can anyone? It is simple network theory, nothing else. Yes, switch on, diode off, inductor charging. Can I say that VDF equal to same Vs? It is directly on, right? So VDF equal to Vs. Yeah. Next, so VDF I got here Vs. Second, during TR to TR plus TF, my load current is decreasing. Fine. Tell me, if load current is decreasing means what is the action in inductor here? Inductor will be discharging. And tell me now, in this circuit, when my inductor starts discharging, at what position my inductor will discharge? Here, when switch is in off state, then to oppose the sudden change in current, my inductor will discharge through freewheeling diode, right? So here, yes, during T equal to TR plus TF, during T equal to TR plus TF, yes, switch will be in off state, diode will be in on state, inductor will discharge, and switch off state, diode will be in on state. Like this, your inductor will discharge. Tell me, if inductor discharge, diode is in a conduction mode, what is the VDF? 0. Voltage across diode will be 0. right? VDF is 0. And third case, third interval, during TR plus TF to TR plus TF plus T0, during T equal to TR plus TF to TR plus TF plus T0. During this interval, what will happen? Now load current is 0. Load current is 0 means your circuit will be at a rest position, right? So this is also off, this is also off, means it is like at TR plus TF, it is your inductor has discharged fully. If inductor has discharged fully, then what will happen? This element is not having energy. If this element is not having energy, then this back EMF will become dominant. This EB will try to circulate current like this, but diode will not allow reverse current, diode will be in a off state, right? So during this interval, switch and freewheeling diode both are in a off state. If both are in off state, then what is VDF? If switch off, VDF off, what is the voltage VDF? VDF equal to EB. VDF equal to EB. Right? Yes. So these are the values of VDF during the different intervals. Now from this, let us draw the plot for VDF. During 0 to TR, VDF is Vs. During TR to TR plus TF, VDF is 0. Next and last interval, TR plus TF to TR plus TF plus T0, it is EB. So it is EB now in every chopping cycle. After that again it is same. So this is Vs and this is EB. Now what is the VDF average? Area under this plus area under this upon periodicity, right? So you can write it as Vs into TR, VDF average Vs into TR plus EB into T0 upon TR plus TF plus T0. Yeah, now put the values here. Vs is 400 volt into TR 10 millisecond plus EB back EMF 300 volt into T0 6 millisecond upon TR plus TF plus T0. TR is 10 millisecond, TF is 5 millisecond and T0, yes, 6 millisecond, correct? Yeah, you can simplify this, you will get the answer. All right. Yeah. Yes. So this is the one question they asked, and similar type of the question one more time they asked. Okay. Right. Yeah. So this is important question. Right. So friends, I think we are running out of the time. So these are the few questions we discussed from the subject power electronics related to the ISRO examination. All the best for your preparation.